Okay. Hello, welcome to the last seminar of the seminar series that we've had for this semester. My name is Jess Kaminsky. I am a recent graduate of the master's program in biostatistics at Brown. For this talk, I will be doing the first half, and then Gabby, who's a PhD student in biostats at Brown, will be doing the second half. Today, we're going to talk about categorical data and inference with categorical data. First, I'm going to introduce and talk about that type of data, what contingency tables are, and define independence. Then we're going to talk about two sample inference methods for proportions, reviewing what we did last time, and then introducing some new things as well. So what is categorical data? Categorical data, to read this quote, qualitative data are measurements that cannot be measured on a natural numerical scale. They can only be classified into one of a group of categories. So categorical data, qualitative data, those terms are interchangeable, and this is different from quantitative data, which is numerical data. So some distinctions of categorical data. So it's data with categories. You can have binary categorical data, so that's data that just has two observations, two categories. So whether or not a patient survives an operation. So for that variable, you could just have yes or no. There are only two possible outcomes. You can also have categorical data with any number of categories. So you could have multiple categories. For example, if you were measuring the severity of an injury, you might have 4 distinct categories: none, mild, moderate, or severe. Now, categorical variables can also be ordinal or nominal, whether or not they are binary or have multiple categories. So ordinal means that they have an ordered scale. So there's an inherent ordering to these variables, so low, medium, or high. Nominal categorical variables do not have an inherent ordering. They're unordered. They're just separate categories. So in this example, mode of transportation, car, bicycle, bus, or subway. There's no way to logically order these and say that one is greater than the other. So with categorical data, we can use contingency tables to display the outcomes and sort of further explore this data. So here we have an example of a 2x2 contingency table. And the variables that we're looking at are gender, and then whether or not that subject supports candidate A. Now, with these two variables, these two binary categorical variables, our subjects can fall into one of 4 categories. And then their counts are listed here. So 240 subjects are male and support candidate A. These column totals give the total number of candidates subjects who support candidate A, the total number of subjects who do not support candidate A, the total number of male subjects, and the total number of female subjects. We're mostly going to be working with 2x2 contingency tables today, but just for an example, I wanted to show you that you could also have a 3-way contingency table, which this is looking at 3 binary categorical variables. So victim's race, defendant's race, and whether or not they received the death penalty. So this one, we just have 8 different cells that our data can fall into, and these are our different totals. These are much less common. A lot of the analyses that you're going to be doing are going to be with 2x2 tables like this, or tables that just have 2 variables but more categories. So it might be 3x2 if there was 3 different categories, something like that. Okay, so what can we do just simply with contingency tables? What can we find out from them? So we can calculate a lot of different probabilities. First, the joint probability. So joint probability is defined as the probability of the intersection of 2 or more events occurring. So it's the and operator. This and this are happening. So in this example, what is the probability of being male and supporting candidate A. That's a joint probability. So it's what's the probability of one of our subjects falling into this box? With notation, it's written like this: male, P, parentheses male, that upside down U, support A. And that probability can be calculated by taking the number of subjects in this cell, 240, divided by the total number of subjects in this study. So that comes out to 24%. The next probability that we can obtain is the marginal probability. This is the probability of a single event occurring. So examples are, what's the probability of supporting candidate A? What's the probability of not supporting candidate A? What's the probability of being male? What's the probability of being female? So in this example, we're going to look at what's the probability of supporting candidate A. So that's what's the probability of falling into this yes column here. So we just take the total number of subjects that fall into that column, 515, and we divide it by the total number of subjects in the study, 1,000. Gives us 51.5%. Okay, next kind of probability we can obtain is the conditional probability. So the probability that one event will occur given that another event has already occurred. So as an example, the probability of being male given that you support candidate A. So if we know you support candidate A, what's the probability that you're male, or what's the probability that you're female? We write these conditional probabilities like this: probability of being male, and this vertical bar is how we say given, probability of being male given you support candidate A. Now, this was presented in one of the very first lectures, but the definition of conditional probability is that it is equal to the joint probability of both the events that you're looking at divided by the marginal probability of the event being conditioned on. So the event being conditioned on is that second one. So if we write it out in the formula, the probability of being male given you support candidate A is equal to the probability of being male and supporting candidate A divided by the probability of supporting candidate A. So if you recall, we got these two probabilities in the first two examples. That was 24% or 0.24, and this was 51.5% or 0.515. That gives us 0.466. So the probability that you're male, given that we already know that you support candidate A, is 46.6%. So these are just some of the basic summary statistics, summary probabilities that we can get from contingency tables. The next thing that I want to talk about before I get into the inference is independence. So the definition of independence is when the occurrence of one event does not alter the probability that another event has occurred. So from our example, our events would be independent if the probability of supporting candidate A does not change based on whether the sampled individual is male or female. Or then the opposite one, the probability of being male or female does not change whether or not you support candidate A. So these two events, supporting candidate A and being male or female, have no effect on each other. They're independent. So if we look at this from the notation and formula perspective, this would mean that the probability of being male given you support candidate A is just equal to the probability of being male. And then the same with the second one. The probability of supporting candidate A given that you're male is just equal to the probability of supporting A. These events that we're conditioning on are independent from these events, so they don't affect each other, and so it's just equal to the same probability that it would be regardless of knowing that secondary information. So just to add a little bit of theory in here, this is Bayes' theorem. Probability of A given B equals the probability of their intersections divided by the probability of B. Now doing a little math, we go to this step by just multiplying by the probability of B on both sides. And then this here is just, we're just flipping the sides. We have probability of A and B equals probability of A times probability of B. We can jump from here to here because if these two events are independent, then the probability of A given B must just be the probability of A. So we know that if two events are independent, this formula should hold true. Okay. So in the context of the example, if gender and support rate were in fact independent, the product of these two probabilities should equal the probability of their intersection. Okay. So now we're going to get into inference, two-sample inference for these proportions. First, we're starting with the normal approximation method. This is what we did last time. We used confidence intervals. We compared the difference in proportions between two independent samples, and we used the central limit theorem to assume normality. So I'm going to quickly walk you through how we did that, what that looked like, and the conclusions that you're able to draw from that first. So using the same data, we have two independent samples, which is different from having two independent events. And we would like to determine if there is a statistically significant difference in their proportions. So is the proportion of males who support candidate A significantly different from the proportion of females who support candidate A? So if we want to determine this, we can write our hypothesis like this. So our null hypothesis is that the difference between the proportion of males who support candidate A and the proportion of females who support candidate A is 0. So if in fact they're the same, then their differences will be equal to 0. And then our alternative hypothesis is that they're not equal to 0. They're not independent. From our sample data, we see that the proportion of males who support candidate A is 48%, and the proportion of females who support candidate A is 55%. Next, we were able to assume normality and say that our conclusions were reasonably valid under these conditions. I presented this rule, which is just the sample size of the first group times the sample proportion times 1 minus the sample proportion. As long as that was greater than or equal to 5, we can assume normality and conclude that our conclusions and inferences are reasonably valid. So for this example, they're both greater than 5, so we can move on to make inferences. So we can construct a confidence interval to test this hypothesis and determine whether or not there is a significant difference. We use this formula, we plug in the values, and we get this confidence interval. The main thing to notice is that this confidence interval does not contain 0. So we have, because it doesn't contain 0, we have enough evidence to reject the null hypothesis that the proportion of support rate among male and females are not equal. We can conclude they're not equal. We're rejecting the null that they are equal. There's a significant difference in proportions of men and women who support candidate A. Therefore, this implies that the support rate varies depending on gender. There is a relationship. So we were able to make this conclusion and run this test using this normal approximation method using a confidence interval. But we can also use contingency tables like I presented to you before. So basically this is the same thing. You should get the same results, but this is just another way to do it. The contingency table is an alternative way of testing the difference between these two proportions. So in this example, we have the same hypotheses. Our null hypothesis is that there is no difference. Their difference is equal to 0. and the alternative is that there is a difference. The difference between them is not equal to 0. So if we knew that the null hypothesis was true, what would we expect to see before we took samples? Well, this is basically just saying that men and women support candidate A equally. If we knew that the null hypothesis was true, what would that mean for the relationship between the support rate of candidate A and gender? It would mean that the support rate does not vary by gender. The support rate, whether you're male or female, is the same, regardless of that. They're independent. So with that, we know this method can test whether or not the proportions are the same and whether or not they're independent from each other. So with the contingency table method, this is the same contingency table that I showed you and that we've been working with. This is considered our observed contingency table. These are the counts of the observations that we observed when we took our sample. Now, to perform a test, we need to use this table, and we also need to generate and use an expected table. So the expected table is the table that we would expect to see given that the null hypothesis is actually true, given that there is actually no relationship between the two variables. So how do we get the expected table? Well, we start by using row and column tables, these marginal counts. So we keep all these the same, and then we're going to fill these in with our expected counts. So how do we do that? If we randomly pick one of these 1,000 people from our sample, the first question we want to ask is, what is the probability that we pick a woman? So here, it's not too difficult because we see that it's just half and half. We have 500 men and 500 women. So the probability of randomly picking one subject and that subject is a woman is 1/2. 500 women out of 1,000 subjects. The next question we need to ask is, what is the probability that this person supports candidate A? So this is 515, the total number of people who support candidate A, divided by the total number of subjects, 51.5%. So again, thinking back to our independence formula, if gender is indeed independent of support rate, what is the probability that this person is a woman and supports candidate A? So the probability of being female and supporting A. So we saw that if they are truly independent, then this probability should be equal to the product of the marginal probabilities. That's going to be 25.75%. So we expect that given the true null hypothesis. So now we can use this, excuse me, to fill in the expected count. So the probability in our sample of being female and supporting candidate A was 25.75%. But we want to then translate that to a number of people that we expect to see. So we just multiply that probability by 1,000, or the total number of people in our sample here, to get 257.5. That's how many people we expect under a true null hypothesis to support candidate A. We can then do this for the 3 remaining cells, and that would look like this. So we're getting the marginal probabilities and then multiplying each of those by 1,000. And then we have our expected table. This won't always look like this. These are the same because we have the same number of men and women in our study, but other times you'll get different numbers for all 4 cells. So in general, the formula for expected counts is expected equals row total times column total divided by grand total. So you can do it both ways. You can get those probabilities and multiply by the sample size, but you can also just plug in numbers to this formula to get all of your expected counts. Now, how do we actually statistically test whether or not these observed values are compatible with the null hypothesis? How close are they to the expected observations? So we can use this thing called the chi-squared or Pearson's chi-squared test statistic, which just tells you to take the sum of the observed minus the expected squared divided by the expected. So for every instance of observed and expected, you're going to subtract them, square them, divide by the expected, and then sum them up. This is typically something that you won't do by hand. R or some other computing language will do this for you, but this is sort of what's going on behind the scenes. And it's just important to note that this test statistic is just comparing those observed and expected, and we're looking at the difference between those. And so for the null hypothesis to be true, we're looking for really small differences between observed and expected. And for us to reject the null and conclude that the proportions are different, we're looking for big differences between the observed and expected values. The larger the difference, the stronger the evidence against the null hypothesis. So just so you can see, these are the observed that we got, and these are the expected. So that test statistic, for example, would be comparing this 240 and this 257.5, observed and expected. And it would be comparing for each pair of observed and expected. You would get 4 values and then add them up to get that chi-squared statistic. So sort of in summary, we have this chi-squared independence test, which is the same thing or another name for the contingency table method, which I've been showing. It's always a two-sided test. This simply just means that we don't care whether the observed is bigger or the expected is bigger. We're willing for either one to be true. We're just looking for differences, regardless of which one is bigger. A brief note on degrees of freedom, Gabby will go into this more, but we have this formula. Rows minus 1 times columns minus 1 gives us our degrees of freedom. So just for this example, that would be degrees of freedom equals 1. 2 rows, 2 columns. So if you compared all those observed and expected and plugged it into that chi-squared formula, you would get this test statistic, and you have this degrees of freedom. And then you get this p-value, again, from R or from some computing language, but what it's doing is it's comparing this test statistic to a chi-squared distribution with 1 degree of freedom, and then seeing where it falls to get this probability. So this p-value of 0.02679 is less than 0.05. So similarly to the normal approximation, at a 95% confidence or a 5% significance level, we reject the null hypothesis and conclude that gender and support rates are not independent, and there is a statistically significant difference between those two proportions. So quickly, just to show you what this might look like in R, this first line is you're generating your observed table by plugging in those 4 values and telling it that those are strung across 2 rows. And then this is saying perform a chi-squared test on the observed table. You'll get into this correct equals false later. But when you run those 2 commands, this is what would come out, which is exactly what I had showed you before. The chi-squared value, the degrees of freedom, and the p-value. So just like the normal approximation method, the chi-squared test is still an approximation method and based on the central limit theorem. So in the normal method, we had that sample size times p1 hat times 1 minus p1 hat must be greater than or equal to 5 to conclude valid assumptions. Here, we need to have every expected count greater than 5. So in each cell, we want the expected value to be greater than 5 in order to conclude that our data approaches a chi-squared distribution, and we can conclude that our observations are and our inferences are valid. And then as with all other tests, the normal one and this one, we need to assume that our observations are independent before we can make any valid conclusions. So for the next part, I'm going to hand it over to Gabby to start talking about degrees of freedom.
Are there any questions? This is a really basic question. With the tables and the sums used to return tables we have written in the table, would you also call it the expected contingency table? Can you repeat it on repeat the question?
So there was a question about terminology, which was you have the observed contingency table and then the expected table. And the question was whether or not you would also call it the expected contingency table. And you could. I think those are just sort of used loosely and interchangeably. Yeah. Are there any other questions? Okay, thank you.
Okay, so Jess kind of addressed the issue of the degrees of freedom, which is actually a parameter of these chi-squared tests that we need to specify. The degrees of freedom, what it does is that the chi-squared is actually a distribution, and the degrees of freedom of this distribution impact the shape of the curve. So it's important that you properly specify it. One thing to note is that a lot of the software that we use to specify the degrees of freedom, to conduct chi-squared tests, actually usually just specify the degrees of freedom for us. So you don't necessarily need to know how to specify this value, but it's just important to understand where it's coming from. So in the case of chi-squared tests, the degrees of freedom are going to be the number of values that you need to specify before you know all of the values of the cell in a table. So what we assume when we're trying to figure out how many values we need to specify before the entire table is filled is we assume that the marginal counts are known. That is, we assume that we know the total row counts and the total column counts. So for this example here, where we have 2 categories for this search variable and 3 categories for this algorithm variable, we assume when specifying the number of degrees of freedom needed that we know the total number of no new searches, which was 7,078, the total number of new searches, which was 2,922, as well as the total counts that pertain to each algorithm. So this was 5,000, 2,500, and 2,500 respectively. So the way in which you can think about these degrees of freedom is that you want to think about it for each row and also for each column. So we start by looking at this 2x3 table. In a table, this table has 2 rows. So what this means is that every single column is going to have 1 degree of freedom. So what I mean by that is if you focus on the first column, which is test 1, since we have 2 rows, once you know the value of one of those rows, so once I know that X value in the first cell, I know exactly what the second value in that column is going to be. It's going to be 5,000 minus X. Similarly, if I told you that I know that the value for no new search and the test 2 cell is, let's say, Y, I'm going to know that the count for the new search test 2 cell is 2,500 minus Y. So since a table has 2 rows, every column is going to have 1 degree of freedom. Once we specify one value, we automatically know what the other value in this table with 2 rows is going to have. Similarly, we've thought about the number of degrees of freedom for each row. If we think about it for what we need for each column, in a table with 3 columns, each row, on the other hand, is going to have 2 degrees of freedom. So for example, if we're looking at the first row, so the no new search row, once I've told you that those 2 entries are X and Y, the first 2 entries in this row are X and Y, once you have that information, you're immediately able to derive that the third entry in that cell is going to be 7,078 minus X minus Y. So I'm talking about this entry here you know that it's going to be 7,078 minus X minus Y once two values have been specified. So yeah, I've been trying to build a little bit of intuition for this formula for degrees of freedom, which is actually just equal to R minus 1 times C minus 1. R is the number of rows and C is the number of columns. So if you have, as in our example, 2 rows and 3 columns, the degrees of freedom that you're going to need is going to be equal to 2, because 2 minus 1 times 3 minus 1 is just equal to 2. So again, if I go back to the illustration in R that Jess was showing for the chi-squared test, and I believe this is the case in most software, you don't need to necessarily specify the degrees of freedom. R or any software usually just computes it for you, and you can see that it says degrees of freedom equal to 1 for this particular example. But it's just nice to know where this is coming from. So if we think about the example with the 2x2 table, this one here that Jess discussed, the reason why the degree of freedom in this case is 1 is because there were 2 rows and 2 columns. So 2 minus 1 times 2 minus 1 is going to just equal 1 times 1, which is 1. So that's where that value is coming from. And again, the degrees of freedom is a value that's impacting this chi-squared distribution, which is what we're assuming when we're conducting the test. So it's a value that if you don't have your software available and you do need to compute it by hand, it's important to know how to do that. So I do want to move on to another form of a test for two-sample inference for proportions. Just discussed the normal approximation method as well as the contingency table method. And Fisher's exact test is going to be a useful tool to have in situations where perhaps these methods that were previously discussed don't work well. So the normal approximation method and the contingency table method, which were again the methods that just discussed, are going to be yielding identical p-values, and they both also are approximations. So what this means is that they rely on the central limit conditions holding. If the central limit conditions do not hold, then you may want to use an exact test instead, because if you're using some sort of method that relies on an approximation, it's important that whatever is needed for that approximation actually holds, because if not, your test is going to yield incorrect results. So what are situations where we can't really rely on the results of the normal approximation and contingency table methods? One case is going to be when the expected count is less than 5. So if you look at those expected contingency tables or expected tables, and you see that one of the entries there is less than 5, then you might want to be alerted that you shouldn't be using the contingency table method or normal approximation method, because you just don't have enough information to use these approximations. Instead, you might want to rely on Fisher's exact test. So let's look at an example to help us illustrate this test and when it might be useful. So in this situation, there's going to be 2 potential causes of death. One is cardiovascular disease, and the other one is some other type of cause of death. And so we're going to consider those who died of CVD as cases and those who did not die of CVD as controls. And we're trying to examine whether the type of diet that you're exposed to, as measured by high salt or low salt diet, has an effect on the cause of death. So are these 2 variables associated? And as you may see, this is the data that you collect in your retrospective study. So you had a total of, let's say, 25 controls and 35 cases. And of these 60 individuals, 7 had a high salt diet and 53 had a low salt diet. So in this case, we're interested in knowing, is the probability of a high salt diet in cases the same as the probability of a high salt diet for controls? Because if the probabilities are different from one another, then it might help us better understand how your diet can impact your incidence potentially of CVD. So when we conduct our expected count for testing this hypothesis, which is this table here, so this table's our expected contingency table, we find that one of these entries, or sorry, two of these entries is actually below 5, which is the rule of thumb number for when you can start to rely on the approximation methods. So since 2 of the counts are less than 5, this is telling us, hey, maybe we don't want to use the approximation methods. We should be using an exact test instead. So this is a situation where you'd want to use Fisher's exact test. And again, even though it's very important to understand the theory behind all of this, I did want to emphasize through this slide that most of the time your computer software is going to be alerting you as to when you're conducting a test that might not be working well or that the approximation might not hold. So I included it in R, but you could also conduct this sort of test in any other software. When you conduct the chi-squared test in R using this observed contingency table, you end up getting this warning message in the bottom, and it's telling you the chi-squared approximation may be incorrect. So the reason why this warning message is coming up is precisely because of the previous slide where we showed that some of the expected counts for these variables were below 5. So that's why when we're using an approximation that needs it to be above 5, it's giving us this warning message. And this is a little bit of a side note, but one thing is that when your software is giving you a warning message, I think it's very tempting for a lot of people to just ignore it and keep on with their analyses. But I think in a lot of cases, it can lead to incorrect inference and just incorrect analyses. So definitely make sure that you kind of look into why you might be getting certain warning messages. In this case, it's because the approximation doesn't hold. So in R, once you get this warning message and you go through and discover that it's because you just don't have enough of an expected count for some of the cells, you might go through and conduct Fisher's exact test. Fisher's exact test does have a huge formula that can help us quantify how to get this p-value here, but it's a very, very complicated formula and it relies on some distributions that we haven't discussed here. So for now, we should just know that it's a tool that we can use with our computing software to calculate statistics of interest. So when we conduct Fisher's exact test in this particular example and for this particular contingency table, we end up getting a p-value of 0.6882. So since the p-value is greater than the significance level we have set, which is just 0.05 for this example, we're going to fail to reject the null. So what this means is that the proportions of a high salt diet among the cases who died from CVD and the controls who died from other causes are not statistically different. So at this significance level, we just don't have enough data to conclude that there is a significant association between this exposure of a high salt diet and the cause of death. And to be honest, you would have reached the same conclusion had you just disregarded this warning message and used the chi-squared approximation, but that might not always be the case for other examples. So that's why it's important to just know that Fisher's exact test can be used. So one other thing that Jess and I wanted to cover today is what happens when you no longer are dealing with 2x2 tables, but rather when you have two variables that have multiple groups. So they don't just have two potential options, but instead there's more than two potential options. So what I mean by this is that rather than dealing with just 2x2 tables, which is what we've been dealing with for this entire lecture, what happens if instead we have R by C tables? So where one of the variables has R potential levels and the other one has C potential levels. So in the previous slides, we've only been focusing on these 2x2 tables, but now we want to try to understand this chi-squared test, which was discussed for the 2x2 tables. We want to understand how it extends to this R by C setting. So we're going to be using this example throughout this section to help us understand how the chi-squared test for independence can be extended to multiple groups. So one of the variables of interest, or our exposure variable of interest in this case, is going to be 3 different algorithms that Google could potentially be using for its search to rank searches. So when you search some sort of word or something on Google, it actually uses specific algorithms, and they're definitely not the ones that we showed here. But it's going to use very, very complex algorithms to come up with a list of results for you. And so here we're interested in comparing 3 potential algorithms to rank searches, to show you the list of results that you want when you type something in. The first is going to be the current version, which is a very, very complex search ranking algorithm. The second algorithm is going to be known as test 1 for this example, and it's going to be a test algorithm that basically increases the search rank of any site that has a picture of a kitten. So let's say the current version, when you type chair in Google, has, I don't know, rank 100 for a site with a picture of a kitten. The test algorithm 1, what it's going to do is that it's going to make that number 100, it might show it to you within the top 5. So it's boosting any site that has a picture of a kitten. And then the third algorithm we're going to compare is going to be test algorithm 2, which is going to be an algorithm that's going to boost the search rank of any site with a picture of a puppy. So yeah, this is just a toy example. So we have these 3 potential exposures. So any type of search that I conduct, I might be put into the first algorithm. So I might come up with the results of the first algorithm. I might come up with the results of the second algorithm, or perhaps the third one. In this case, since we have an exposure with 3 potential levels, we're going to be looking at an outcome with 2 potential levels. One is no new search, and the other is new search. The reason why this is our outcome is because this is a measure of user satisfaction. So the reason why we might care about exploring these different exposures or different algorithms is because Google wants to make sure that its users are satisfied with the results of a particular search term. So again, if I looked up the word chair, Google wants to know whether I'm happy with the results that came up when I searched the word chair. And we're trying to determine, is test 1, test 2, or the current algorithm the best at giving me the most user satisfaction? So in this particular toy example, the way in which we're going to quantify that satisfaction of having searched something and being content with the results that I obtained is going to be through the new search variable. The new search variable is going to have 2 levels. One is no new search. That means that when I search the word chair, I ended up liking something that came up on my page, and so I never went back and searched again. And the other level is going to be new search. So what that means is that when I searched the word chair, I didn't like the list of results that came up, maybe because it was a bunch of pictures of kittens or puppies, and that's not what I was looking for. So instead, I went back and I tried another search. So again, this new search variable is going to quantify how satisfied I am with the results of a particular search term. And having no new search is actually a good thing in this context, because it means that Google was able to successfully capture my search term. So again, in this case, we're not dealing with a 2x2 table. We're actually dealing with a 2x3 table, because the new search variable has 2 potential levels and the algorithm has 3 potential levels. And what Google is going to care about in this case is, are these 2 variables, so is algorithm and new search independent? So for different algorithms, is the percentage of users satisfied with each algorithm the same or different? So for example, if the percentage of users satisfied with test algorithm 1 is higher than the percentage of users satisfied with the current algorithm, then this might show Google that they should be changing their search algorithm to test algorithm 1, which boosts the rank of any website with a kitten. So in order to test this example, we're going to be pretending that we're Google and we're interested in comparing these different search algorithms. So what we're going to be doing is that there's going to be 10,000 individuals or searches that are taking place, and we're going to allocate 5,000 of these to the current algorithm, 2,500 to the test algorithm 1, and 2,500 to test algorithm 2. So again, as a user, if I look up something, again, trash can or something like that, I might be allocated to the current one, I might be allocated to the test one, or to test 2, and this is completely random. So let's explore potential observed results. So this would be our observed contingency table, but this is just a potential one. So if 5,000 individuals were allocated to the current algorithm, 2,500 to test 1 and 2,500 to test 2, which is what we previously discussed. And we found that of these 5,000 in the current algorithm, 4,000 did not conduct a new search. And of the ones in test 1 and test 2, 2,000 did not conduct a new search. Then the probability of no new search is equal to 0.8 or 4/5 for all of the test algorithms. So what this means is that regardless of the algorithm that you use, the proportion of new searches or no new searches is going to stay the same. So if this were our results and we were Google, we would say, you know, it seems like all of these algorithms have the same user satisfaction. And that's an important thing to know because that might motivate us to just keep things as they are because there's not really any motivation to changing things. If on the other hand, our observed table looked like this, so the probability of no new search under the current algorithm were 4,000 over 5,000, which is again 0.8, while the probability of no new search in test algorithm 1 is 2,500 over 2,500, which is 1. And then the probability of no new search in test algorithm 2 is 1,500 over 2,500. What we'd be getting is that the proportion of satisfactory results is 80% for the current algorithm, 100% for test 1, and 60% for test 2. So if we were Google and we had observed this table, on the other hand, we might think to ourselves, hey, maybe we want to move to test algorithm 1, the one that boosts the search rank of pages that include a picture of a kitten, because it seems like people are very, very satisfied with this algorithm. So a lot of the times, though, the issue really comes because things aren't as clear as they are in this table. A lot of the times, you need to be testing these hypotheses in situations where it might not be as clear cut. And that's where these chi-squared tests and hypotheses tests come into play. So the hypothesis that we're effectively testing in these cases is, are the algorithm and new search variables independent? So the null is that they're independent and the alternative is that they are dependent. And as mentioned for the 2x2 case, we can actually test this using chi-squared tests. So we were actually pretending to be Google, and when we conducted this experiment, these are going to be our observed results. And under these, So these were our observed results. And in order to get our expected count table, one way of doing this, which is a little bit different from what Jess discussed, but it's the same idea, is we're going to be using our observed results and comparing them to the proportions. But anyhow, the idea is that we're going to be comparing the observed results to our expected results. So our observed results was that the probability of a no new search was 0.7078 across all 3 algorithms. And what this probability is showing us is that if all algorithms perform the same, this is the probability that we'd expect to see for all 3 values in the top row. Similarly, if all algorithms perform the same, we'd expect to see this 0.2922 in the bottom row. So using this proportion concept, which is slightly different than the expected count one, but yields the same results, we end up getting our expected count table, which is this one down here. And again, it's the same idea as the other one, but we just did it a little different. So I think this illustrates things the best. As Google, we observed this first table, but under the null hypothesis of the search variable and the algorithm variable being independent, we're able to derive this table below. So as Jess explained, the chi-squared statistic is able to capture just how different is what we observed from what is expected. So again, what the chi-squared statistic is trying to capture is it's going to be summing across every single cell in this table, and it's going to be taking the difference between the observed value and the expected value in the corresponding cell. So in this case, our chi-squared variable, our chi-squared statistic, is going to come up with 6 different terms. We didn't write all of them down, but the first of these terms is going to be 3,511, which is the observed count, minus the expected count, which is 3,539 squared, divided by the expected count for that cell. And then you go all the way to the last row and column, and you end up doing the same thing. So it's 682 minus 730.5. So I think what I'm trying for people to understand is that regardless of your 2x2 table or 3x2 table or any table that you're dealing with, what the chi-squared test is doing is that it's comparing 2 contingency tables. One, which is what you'd expect under the null hypothesis, and the other, which is what you actually observed in your experiment. So anyhow, when you end up adding up these 6 terms corresponding to the 6 cells in our table, we end up getting that the chi-squared value is 6.120. So we now want to obtain a p-value. So we can get this p-value using this chi-squared value of 6.91, as well as the degrees of freedom. As I mentioned, this is a 2x3 table. So the degrees of freedom is going to be equal to 2 minus 1 times 3 minus 1. So in this case, the degrees of freedom is 2. When we end up getting our p-value, we find that the p-value is 0.0469. So we're going to be rejecting the null at our significance level of 0.05. This leads us to the conclusion that these 2 variables are in fact associated. The algorithms don't have equal performance when it comes to this user satisfaction variable. Of course, we could have picked other variables as the outcome, but with respect to the one about the new searches, it seems that the algorithms do not perform well. So what we can end up finding, and it's actually, it can be seen through the tables as well, is that the algorithm that I've been calling test 2, which is the puppy algorithm, does slightly better than the current algorithm. So if you were Google and you were to look at all these hypothesis tests and everything, you might want to, instead of using the current algorithm, you might want to use the puppy algorithm instead. So again, you could do all of this in R, but it's just very important to understand the theory behind it. If you were to just plug in your observed contingency table, which is comprised by these 6 values, if you were to just plug it in to R and then ask it to conduct this chi-squared test, then you'd end up getting the same p-value and the same test statistic and degrees of freedom as what we had discussed. So one thing to note is that very, very similar to what was discussed for 2x2 tables, the chi-squared test for independence when it comes to 2 variables that have multiple groups is an approximation method, and it's still based on the central limit theorem. So similar to our rule of thumb for 2x2 tables, we can use this chi-squared test for independence when the expected cell counts are all greater than 5. If this is not the case, then you should be using, again, Fisher's exact test. Additionally, there's other assumptions that should be thought about when you're conducting these tests, such as assuming all observations are independent or that the sample that you're drawing from is a random sample from your population of interest. So yeah, it's just important to keep these things in mind as you're conducting your analyses. So to conclude, we wanted to provide 2 different images that we actually found online about how, which different tests you might want to conduct when you're thinking about doing hypotheses testing for different types of things. I think this was something that somebody had mentioned having some interest in. The 2 that we found that we thought were the best were this one and this one. And I'd be happy to send the link for both of these if people are interested in having them. I think we discussed a lot of these, Jess in particular in the previous lecture discussed a lot of these. So in the previous lecture, Jess was focusing mostly on continuous data. So she didn't go through all of these, but she went through a lot of these. And then here we discussed all of these, except we did not talk about McNemar's test. But yeah, we just thought that was a good way of concluding this section. Thank you so much for attending these seminar speakers, and please let us know if you have any questions. You can reach Jess or I by email if you have any suggestions or comments. Thank you. Are there any? Oh, thank you. Okay. Should I hit? Oh, thank you.
Yeah, you can hit stop broadcast.
Stop share. Cool. Oh, there I am. It's done.